Yeah.
For example, if we are in a symmetry interval,
Yeah.
this covariant derivative include also the covariant derivative of the whole thing.
Yep. You'd have to add, yeah.
Okay, and in this case, this is just a singular, right? I mean, pi is not
Yep.
so I have to enter the pi quantity.
Yeah, so in this case, the pi quantity will correspond to the y coordinates. And
Can you also specify why, when we write the Coset representative, we put also the exponential of the
right. So basically, you have to exponentiate any piece which transforms nonlinearly. So normally in an internal symmetry, only the pions transform nonlinearly, but coordinates transform nonlinearly on their own, right? So the classic example of a nonlinearly representation is just x under translations. So x goes to x plus a. So the symmetries which are represented nonlinearly should be exponentiated, and that's what makes coordinate special. So the space-time symmetry means you have to exponentiate not just the broken, but any unbroken guy which transforms nonlinearly. Okay, so take a second to write down what I have here. So just since we're a little bit behind schedule, I wanted to get a little jump. So this is just a review of the Coset construction for the finite-sized object made of whatever it is. Could be anything you wish. It has some internal frequency oscillations that the effective theory cannot properly describe, right? So this theory only describes the physics on time scales long compared to those oscillations. So think about a really stiff spring, right? So you can't ask questions about measurements on time scales of order of the period of that of the spring. So that's the limit of this. The cutoff, if you will, even though this is a classical theory, is the square root of k over m frequency, right? So we're only allowed to look at resolutions much larger than that, in which case you can see that the short distance physics, short distances, meaning small time scales, washes out. So if I study the system over periods long compared to that frequency, I won't see those oscillations at all, right? By the way, this is an example, a classic example of what's known as decoupling. So those of you who have studied 2 semesters of field theory learn that when you have a massive particle in the spectrum at energies much lower than the mass, the effect of that mass becomes empirically irrelevant, right? This is, again, a consequence of locality. But that's not a quantum mechanical statement. That's actually a classical statement as well. So we usually think about, I integrate out fields, heavy modes, and those fluctuations are relevant. But it's not true. This is a classical statement as well. This is a perfect example, right? So if I have a device which can only measure things on long time scales, I can see the fact that these particles are attached by a spring. Right? The spring, the frequency of the spring is too short for us to measure, and therefore it decouples. Right? If you were an observer who had very crude instrumentation, you would not be able to even know that these particles were correct. You would say this is one particle that rotates and translates, and it doesn't have any internal. So there's nothing mysteriously quantum mechanical about this notion of decoupling, or even the idea of renormalization, which we think of as having to do with quantum oscillations, or in the context of critical phenomena, thermodynamic fluctuations. That's not right. Renormalization, we will talk about classical renormalization. So all the concepts that we learn about as high energy theorists in field theory books, I shouldn't say all, but many of the big concepts like renormalization and decoupling, even the renormalization group, which we always think of having to do with fluctuations, is actually much more general than that. Okay, and we'll talk about how that occurs in classical systems. So this is all classical physics. Okay, so here's what we extracted last time. So the broken symmetries are the rotations, the translations, and the boosts. The unbroken symmetries are M, or particle number conservation, right? And H in the Galilean group, right? So, so I was told yesterday at lunch actually that Galileo's house is right here. Did you guys know that? No, so I think we should all make a pilgrimage to Galileo's house. We can. It seems fitting. I didn't realize that. Everything I'm doing is the Galilean group, and that seems fitting for this setting. These were the covariant derivatives which extracted in the gauge fields. We said, so this term is the 1/2 mv squared. And then we said we can write down an action. So this was the West-Zumino term, because this thing varies by a total derivative. This is now we broke rotational symmetry, so we do not have to write down anything H, which is rotationally invariant, because H doesn't include rotations anymore. So I'm allowed to write down anything, doesn't have to be rotationally invariant. So this Iij are just a bunch of numbers, which I don't know and I have to fix from experiment. Okay, and of course it corresponds to the moment of inertia tensor, right? And then I could write down something which goes like dA to I with some arbitrary number of arbitrary coefficients in front of it. Okay, so that's the first thing I might write down. But if you look at dA to I, it's proportional to x double dot. Okay, and someone brought this up yesterday. I hadn't planned on covering it, but I figure since this is a good opportunity to discuss it. So I think I was missing a dot here yesterday, which I should have fixed at the end. And I claim that you can ignore these operators, and why is that? It's because x double dot at leading order in the equations of motion is 0, right? So what gives you the right to use the equations of motion in Lagrangian? And that right is given to you by the fact that the coordinate is the world line which you choose to parameterize the motion of the coordinate is a coordinate dependent statement, and I'm free to shift my coordinates. So if I claim, I claim in general, so here's the kinetic term where I've done an integration by parts to make things clearer, right? And I'm adding this is some OI that depends on x. It can be any operator that you want. But it's proportional to x double dot. Okay? But if I shift the world line by this amount, and you can plug it in, then it will cancel this term. But it'll add some terms of order c squared. So I claim, first of all, that this term, we're going to say that this term is a subleading term because it's a higher dimensional operator. So if I make this shift, it will cancel this piece, give me back this piece, and it will generate some c squared terms here. Okay? So it's not that the effect of a term which is proportional to the leading order equations of motion gives you 0. Okay? It's just that it can always be shifted to a higher order term. Okay? So what's really interesting is that this holds quantum mechanically. Okay? So this is so if you have an effective field theory and you have a higher a dimensional operator which is proportional to the leading order equations of motion, you can eliminate that operator and throw it away. Now that seems crazy because in a quantum mechanical process, you're not always on shell, right? The equations of motion are not obeyed during a virtual quantum mechanical fluctuation. So it would seem naively that shouldn't be allowed, right? Because quantum mechanical processes are inherently off shell. However, a little bit of thought should lead you to the conclusion that maybe that's a misnomer. So the reason is because if you think about it in terms of the path integral, the fields are just variables I'm integrating over, right? So they're just dummy variables. So why shouldn't I be allowed to shift them in my action any way I want? And the answer is you can. Not everything will be left invariant, but all physical quantities will be left invariant. So if you're interested in, so this is called the equivalence theorem, or the equivalence principle, even though it's not, has nothing to do with gravity. And so I should also say, so I have some TASI lectures from way back, I don't know, like 2000 something. And in there, a TASI lectures on effective field theories, in there I give you quantum mechanical proof of this, that these shifts. My phone? So if you're interested in the proof of that, it's a well-known proof, but I give sort of, I hope, a simple explanation of the proof in those lectures. Okay. So that's called order reduction. And so as an exercise, it would be good if you, for yourself, figured out what was the first non-vanishing, non-canonical kinetic contribution to, in other words, what's the first term that doesn't vanish by the equations of motion beyond the kinetic piece for the rotational and kinetic degrees and translational degrees of freedom. So, and then it would be interesting, actually, I haven't worked this out, so this is something that would be fun to play with. There are lots of interesting questions you can ask about this theory. So for instance, there could be various power counting schemes. So what's bigger, the rotational velocity or the translational velocity? There could be a hierarchy in those. And then if I look at higher dimensional operators, I can figure out which ones are big and what limits and so forth and so on. And then there are interesting questions you could ask about what do these coefficients mean? And then if you wanted to, you could play with it further and choose a model for a spring and a UV completion, and then you could try to figure out what those values of those coefficients are. So there's lots of different exercises you could do that would be useful. Okay. So now we said if I added another, what happens if I start to add more and more oscillators? Does anything new happen? Anything interesting in terms of the low energy or low momentum excitations of the system? And the answer is yes. Something very interesting happens in a certain limit. Okay, suppose I add another oscillator. So now let me look at we wouldn't expect much anything new at this point, right? There's going to be a set of normal modes now, which we can write down. So the frequency of the normal modes are, there's 0. Let me just talk about one dimension. I'm not worried about rotations at this point. Just in this direction. If I only consider motion in this direction, and then there's square root of k over m, and then there's 3 square root of m. We have 3 normal modes now. Nothing really changes, right? We can't describe these modes. We can describe the translational mode. If we wanted to let it rotate, we could let it rotate. And then nothing really would change except the Wilson coefficients. I haven't used that term. So the coefficients of the operators are called Wilson coefficients from Wilson's original description of the operator product expansion. So there's a deep connection between, of course, the operator product expansion, for those of you who know what that is, and effective field theories. And so the coefficients of those operators are called Wilson coefficients. And if I change my ultraviolet theory, which was what I would be doing by adding another spring, then I would just, there's going to be a different moment of inertia tensor, there's going to be a different mass, and all the other Wilson coefficients are going to change as well. So that doesn't seem, so we haven't really learned anything interesting. However, what happens if we turn this into a chain and we let that chain become arbitrarily large? Then something interesting happens. And the question is why? First of all, let me tell you what happens. So then we get a series of normal modes. So okay, so let me take the limit of large n, where n is the number of oscillators. Let me take the spacing between these oscillators is going to be A. And we're going to assume that K is this is in the equilibrium position, and K is the spring constant, as it was before. Okay? So in that limit, we get that the normal modes have frequencies which look like this. Where Q looks something like a momentum, but is quantized okay? So n takes on values 0 to infinity. L is the length of the spring. So n is the number, counts the number of springs. In other words, this is the nth, n plus 1, n plus 2, so forth. So L is equal to n, or big N A. And n counts, n goes from 0 or 1 to n. Okay? Okay, so why is this interesting? So what happens if we take L to infinity? Right? For small q, so for small q, so n fixed and L go to infinity, omega goes like q. So if we think about q in the large L limit is becoming a continuous variable. And of course, what's happening is we're getting traveling waves, right? And so we now have a new gapless mode, which seems a little odd, right? Because we thought we got gapless modes when we broke symmetries, but I haven't broken any symmetries, apparently, right? So why do we get an additional gapless mode? We thought we would generate gapless modes as we broke more symmetries. And the reason is that as we've make this chain arbitrarily long, and we look at distances short compared to the size of the system, but large compared to the size of the springs, we have a new symmetry. We have a translational invariance, an internal translation invariance that is inherent to that particular system. Because it doesn't matter if I look over here or if I look over here, the system looks identical, right? So I have an emergent symmetry in this large L limit. And what I'm going to show you now is that emergent symmetry is spontaneously broken. And as a consequence of that spontaneous breaking, we have a new Goldstone boson. And that Goldstone boson is the phonon, right? The acoustic waves of the spring. And we'll actually generalize this now to 3 dimensions. And that will give us a model of a solid, right? Because that's what a solid is. Now, it's kind of interesting to ask, well, I claim I have translational invariance, and clearly a solid, if this is really supposed to be a model of a solid, there's something funny going on, because there's no way a solid is this uniform, right? A solid is made out of crystals, and each crystal has a different structure, which different masses of ions at different points. So we could ask a question, well, does this really model a solid? Because a solid doesn't have this exact translational symmetry. So if I consider an inhomogeneous lattice, so let me take so I'm going to vary the spring constant, so forth and so on. So it's more like a bipartite lattice in the sense that it's got two different spring constants. And now I've further reduced my translational, and it looks like I've lost my translation variance. So I should lose my phonon. But if you do the calculation for what the long wavelength modes look like, actually, you know what? The way I did it is not by changing. Instead of changing the spring constants, let's change the masses. Well, we could do either one, but let me call this M1, M2, M1, M2. And I did that just because that's the original calculation I did. This look like 2k mu M1, M2 to the 1/2 A Q. Okay? So you still get that mu is the reduced mass. Okay? So you still get a zero mode, even if I break the translational invariance. Okay? But this shouldn't be too surprising. Yeah.
Don't you still have translational invariance?
You do, but only at a larger scale.
Yeah.
Right, exactly. So, and I can imagine putting M1, M2, M3, right? And then I would also have, but as long as I'm looking at large enough scales, all that stuff gets coarse-grained. I can't see it, right? This is why, this is why if you look at a pointillist painting from far away, it looks continuous, right? It's coarse-grained. So even though I've lost translational invariance, as long as I'm looking at distance scales large enough and at time scales large enough, all that stuff just gets averaged out. So all that will do will be to change the Wilson coefficients, right? In my effective field theory. Yeah.
So there's no difference between having M1, M2, M3, M1, M2, M3, or 1, M2, M3, M2, M1?
Yep. Yeah. Yeah, so right. So things can get arbitrarily complicated. Think about a theory of a fluid, right? So a fluid is made up, it can be any arbitrary fluid made of any molecules, types of molecules you want. They all have phonons, right? And so the theory of hydrodynamics is exactly based on the idea that at distances large compared to the microscopic physics, it doesn't matter what it's made out of, right? You will always get a phonon. So even though it doesn't look translationally invariant at short distances, at long distances, as long as it's a homogeneous system, right? So in other words, if I took a fluid and I changed the density at long distances, if I had some sort of partition which separated different types of fluids, then as I push that partition closer and closer together, I'm going to lose more and more of what I would call the sound wave, right? But the universality of hydrodynamics, why do all fluids behave the same? Not all fluids, but generic systems of fluids, is because at long distances, everything just gets coarse-grained away. Now, for those of you who are aficionados in field theory, especially high-energy theorists, this seems like a strange thing, because normally we'd say, if you break a symmetry at short distances, it will show up at long distances, right? So in other words, say electroweak symmetry were broken at the Planck scale, it would certainly change the long-distance physics dramatically, right? So what's the difference between this and that? So I'll let you think about that. Okay. All right, so now let us build, in this first 45 minutes, let us build an effective field theory which describes phonons in a solid. Okay? Oh, wait, before, I wanted to give one other exercise. I realize, so you should pick and choose the exercises. Obviously, you don't have to do any of them if you don't want to, but pick and choose the ones that you find interesting. So I want to give you a whole bunch. So one is, so build the coset for relativistic point particle. Okay? So take the Lorentz group and build the coset. In this case, we'll find, of course, that you'll find that the Einbein is no longer equal to 1, as we discussed last time, and the Einbein will play an important role in the theory. So it's worth doing that exercise. Okay. So let's talk about the EFT of solids. And let me give you a citation to, so this was a paper by, this was first discussed in a paper by Penko et al. And let me give you that number. In case you want to look at it in more detail, then I will go into here. It is 1405. '7384. So this has applications. In fact, if you want to cheat and look up the answer to this exercise, it's in this paper. So if you get stuck, you can look there. Let me give you one other citation to, so there's a paper 17, which just came out, 12/07795. Which discusses the issue of what happens to framids, why systems do or do not manifest Booth-Goldstone bosons. And it also discusses non-derivative couplings of Goldstones. So that's something I don't think I'm going to have time to talk about. We actually saw it. If you remember, d eta, I should have mentioned this at the time, was x double dot I plus epsilon ijk x double dot theta jk. So this eventually you could eliminate this from the equations of motion, but you can see that this Goldstone, the rotational Goldstone, is not derivatively coupled. It has no derivatives on it. So this is the first example of a case. I promised you yesterday I would show you that the idea that Goldstones are always derivatively coupled is incorrect once you allow space-time symmetry breaking. So there's an example right here. This paper discusses that issue in more generality. Okay, so let's talk about solids. So we're going to talk about a three-dimensional solid, just because we can without making life any more complicated. So so now we have enhanced symmetry. So when we take this limit where we have an arbitrary number of oscillators, we have we have this system, and it could be an irregular lattice. I'm just drawing it regular. It doesn't have to be regular. As long as at long distances it looks homogeneous, right? So at long distances, this thing has a rotational as well as a translational internal symmetry. So we have an internal and I'm going to use, I have to distinguish, so I have to come up with a good naming scheme to distinguish between internal symmetries and space-time symmetries. So, so I'll call the internal rotations R to distinguish it from L. And I'll call the internal translations Q. Okay, so these symmetries are unique to the system. They have nothing to do with space-time. So that's why we're going to call them internal symmetries. There's also the space-time symmetries, right? So, we're going to call L the space-time rotations, as we did before, of the Galilean group. And we're going to call T, I think I call it T. Or P, the space-time translations. Okay? So the question is, what symmetries are broken by this system? Yeah?
What do you mean by what happens under the internal translation?
Internal translations is just the idea that if I look at the system, I shift this this coordinate to this coordinate, it looks exactly the same.
Wouldn't that be a coordinate?
So yeah, so it's like having a if you think about a rigid rotator, there's a body fixed coordinate system and a lab coordinate system, and so this is more like a body fixed transformation as opposed to a lab transformation, right? So you'll see in a second, things will become clearer. Let me just, in a second, when I show you how to describe the system. So let me, I think if it doesn't answer your question, we'll come back to it. So let me define phi I of x and t as labeling the particle, so giving the position, so this I is going to be 3 numbers. So given a coordinate, so I'm going to put this thing on a coordinate grid. This is my x coordinate system, right? So I choose an x, and when I choose an x, it's going to give me this phi I is going to give me the position of that particle, right? So this labels, it's like I put a number on each one of these guys. Let me call this, 1, 1, 1, 2, 2, 1, something like that, and I give each one a label. So at any given x, it tells me which particle is sitting there, right? So this is the label of the particle. Okay, so this hopefully will answer your question now. So now, what symmetries of the system do I have? So x is this. It tells you the boxes are sitting on this coordinate system, right? And I can choose this point and ask what particle is sitting at that point at what time. That's what this map will tell me. Okay? Now, so the question is, what is the ground state of the system? So the ground state on the system, I'm going to take to be the equilibrium value of this system. So the ground state, expectation value, I'm going to be is just xi. Okay? In other words, if I look at, I'm going to label my points exactly by their coordinates in this space-time grid. And that's obviously a very wise choice. So that is, when the system is not moving at all, it's in its ground state, it's unexcited, that is the, and I'm going to write this as delta I A x A. Okay, so the i's, remember that I'm going to use big I's to label this field and capital Roman to label these coordinates and non-capital Roman to label the space coordinates. Okay? So the question is, what symmetries does this break? Well, clearly it breaks space-time symmetries and it breaks internal symmetries, but it preserves the two, the diagonal subgroup, right? And the same thing goes with rotations. So in other words, if I rotate my coordinate system and then I rotate the solid, then nothing changes, right? If I translate my coordinate system and then translate the solid, nothing changes, right? So it's what's happened, it's broken to a diagonal subgroup. So the symmetry breaking pattern is SO3, I'll call it I for internal, cross SO3 space-time goes to SO3 internal plus space-time. And then the translational, the three translations, internal space-time goes to the diagonal subgroup. Okay? Did that answer the question? Yeah. Okay. Okay, so now we know the symmetry breaking pattern, and I'm going to jettison this field. I don't care about it anymore. Why? Because I know how to build an action using the Coset construction, right? But the thing that we've learned from this is by enhancing the symmetry, by looking at a macroscopic object, I've broken that enhanced symmetry in the ground state, and I've gotten a Goldstone boson. That's exactly what we found when we looked at the spectrum, right? We saw that as we took the number of springs to infinity, I generated a new gapless degree of freedom, right? And that gapless degree of freedom is nothing but the phonon. Okay? So now let's build a Coset construction for this system. Any questions? So I hope you're now starting to see why the world is just a bunch of Goldstone bosons, right? And then why the first thing you should be learning in school is not Newton's law, but Goldstone's theorem. Okay, so let's look at the symmetry breaking pattern. So, so what's broken? Q, T, or P, sorry. L and R, right? And boosts. Right, and what's unbroken? H and M, L plus R, and Q plus P. Okay, now let's build our Mark-Harton form by first writing down U. Now, when we choose U, we have a little bit of arbitrariness. We have lots of arbitrariness. One is the order, which we talked about yesterday. But also, I'm always free to exponentiate an unbroken symmetry as well, because its action on the vacuum gives nothing. And so the question is, well, should I exponentiate both of these? and both of these, right? Well, I'm always free to add the sum. So I can choose to either one or the other. And here I can choose either one or the other. And I should choose the one which makes my life the simplest. And that just comes from a little bit of experience playing with these things. So I'll show you the one that I chose. So I took u to be e to the I p dot x. I'll tell you what that p is in a second. K dot eta, our usual friend. Okay, so p bar here, so p bar is composed of h and the unbroken translations. So this is q plus p. Okay, so there's a little problem here because the bar, actually, so let me, Okay, so I had some freedom here, and this is just one choice, because I'm always free to add anything which is unbroken, right? So I'm free to add the sum of this, and I'm free to add the sum of this in exactly the way to maneuver either left or right pieces or Q and P pieces if I wanted. So now notice that this is actually the coordinate. This is no longer, this pi, you can think of this pi as, remember before the translations had for a point particle we had this, right, yi of t, but now I is becoming a continuous coordinate, and this is being lifted to pi x and t, where this I is that continuous, that I labeled a continuous coordinate. So that's the way you should think about it, right? And this x is the full coordinates. These are not functions of t anymore, so don't get confused between that. So we lift, this used to be just t here, right? But now it's t comma x3 vector. This used to be y I of t for a point particle, and now it becomes an infinite number of point particles, meaning those, the phonon field. Okay, now what I would really like to do is work out all the covariant derivatives and all the Vierbeins for you, but I can't because we simply don't have enough time. So the method of doing it is exactly the same as what everything we've been, there's nothing new here before, it's just more algebra. Okay, so I don't think there's anything inherently useful for me to spend however long time it would do to do all the algebra for you. But let me at least write down what the results are. Now, in this case, we have, since we're in higher dimensions, we have to write down a non-trivial Vierbein. So in this case, we have u minus 1 d mu u, as opposed to just t, because now we have all three coordinates as well as time. And this thing is equal to e a mu, and then all the objects which we had before, but now labeled by a. So now we have a non-trivial Vierbein. Now, the question is, do you think this Vierbein is going to be non-trivial anymore, even in the non-relativistic limit? So what happens to x under a boost? Does it change? A Galilean boost? Sure. X goes to x plus vt. So the Vierbein should now be non-trivial, and the Vierbein should relate the unboosted system to the boosted system. So not surprisingly, if I wrote down the answer for the Vierbein for you, it looks something like this. So E00 is 1 because time doesn't change under a boost. E0I is eta I, the boost parameter, and Eij is delta ij, and Ei0 is 0. So this is, I don't want to burden you with exercises, but for those of you who are enthusiastic, this would be a good thing to do. The gauge field looks the same. And now has a non-trivial I index as well. And let me tell you what the covariant derivatives look like. So I think I was calling this big D before, but I think you know what I mean. It's a covariant derivative. D0 pi I is pi I dot minus eta A dA pi I plus theta epsilon, if I here I did it in 2 dimensions. Epsilon j I j, let me put them all up, k eta A, sorry. Okay. Okay, and then dj pi I is dj pi I plus I epsilon k epsilon I j k. And the covariant derivative of the Fremon is just simply the gradient, and similarly for the Goldstone for rotations. Here I'm interchanging capitals and Romans freely because of the delta function which sets them equal, so there's no distinction between the two anymore. Okay, and so now you have everything you need in order to build your Coset action. And we have to impose an inverse Higgs mechanism, as we did before, to allow us to get rid of the boost Goldstone. So the inverse Higgs mechanism, we will choose to set delta 0 pi I to 0. And you could ask, how do you know where to choose your inverse Higgs? And the answer is, you always look for the covariant derivative that has something which is linear in the field with no derivatives on it. So I set this to 0. This will allow me to solve for eta I. And if I set this one to 0, what this, do I have the unit ij? Is there a dot there? Yeah. And if I set this one to 0, allow me to solve for theta. So I can set this to 0, and I'm going to set epsilon ij dj pi I to 0. So this allows me to solve for eta, and this allows me to solve for theta. So the only degrees of freedom I have left over are the pi's. So for instance, if you tried to choose this, I don't. So let's see. If I chose to do that, I would know that theta dot was 0. So you don't want to choose anything where there's derivatives acting on the field, because then if I try to solve for the field, there's an ambiguity. I have to integrate it, right? So yeah. So that's an interesting question. So you're right. It shouldn't matter. The problem is that if you choose unwisely, you're going to make your life miserable. Okay. So, if you look at lambda phi 4 theory, right? The S matrix is independent of your choice of variables. I could choose a transformation. Lambda goes to lambda plus sine, phi goes to phi plus sine phi. That will not change any of the S matrix elements, but it's going to make your life miserable, right? So the mathematics is smarter than we are. So it doesn't matter what you choose for your variables, but if you want to actually get a result, then you should spend time thinking about what the simplest choice of variables are. It's just like any other problem in classical mechanics. If you choose Cartesian coordinates for a system with spherical symmetry, you're going to make your life miserable. So in field theory, the same is true. It's just that when we learn field theory, we don't, this isn't something that we really concentrate on, but you can change variables any way you want, right? We always think of phi 4 theory, right? But if I change variables, not only will I leave the answer invariant, but the symmetries still have to be the same as well. It's just that they'll be completely obscured, right? And the freedom to change variables actually plays very important roles in many field theories, not just formally through dualities, but also in effective field theories such as SET. Many of you probably have heard of. You redefine fields all the time in terms of Wilson lines, and you make your life a lot easier by doing so. Anyway, that's neither here nor there. So if you were to now build the action, you're going to get a kinetic term for the phonon, right? And then all the anything you can write down, which is consistent with the unbroken symmetries, you will get all the interactions between phonons as well. Okay? And this is just a solid, is just a theory of phonons. Okay. So we're going to shift gears. So we're going to change topics now. And so let me just stop and see if there are any questions before we do that. So I think this is a logical, this subject goes on forever, but I think this is a pretty good logical stopping point. So are there any questions before we move on? Okay. All right. Yeah, good. Yeah.
We built our U operator in this way, but generators are not commuting with each other.
Correct.
So we could choose another form.
Correct.
Why we choose this?
Because that's the one I chose.
Okay, so
If you chose another one, you get the exact same answer. So actually, again, if you're ambitious, do it 2 different ways and see what happens. Okay, so we've so far just been studying theories of Goldstone bosons, but of course there are other gapless modes, and that is gauge fields. And now we're going to study the theory of gauge fields. So if you look at that reference that I gave you, they talk about how to gauge the coset. So how do you gauge the coset's exactly how you think you would gauge the coset. So now what's interesting is actually, I'll look up the reference, I'll give it to you tomorrow. There's a paper which actually explains how to think of gauge fields as Goldstone bosons in the Coset construction. So this isn't really new. I think people have realized, for instance, that in condensed matter systems that you can realize the phonon as a Goldstone boson. The photon. But in general, there's a way to think about any gauge field as actually a spontaneously broken, as a consequence of spontaneous breaking of symmetry, and I'll give you the reference for that tomorrow. Okay, so now we're actually, what we'd like to do is apply some of our reasoning to a real-world problem, which is gravity wave physics. So this is obviously a topic which has gotten a lot of attention lately, and will continue to get attention for a considerable amount of time. This is actually, we're witnessing the birth of a new field of science, and we're just in its infancy. So I think it's a very worthy subject to spend time on. And it'll also allow us to go beyond what we learned in effective field theory. So right now, we learn in effective field theory where there's essentially one power counting parameter, which is momentum or energy over the cutoff, right? But there are systems which are much more complicated than that have multiple power counting parameters, right? So I can give you a litany of lists of different effective field theories, each with a different set of power counting parameters. And furthermore, there are theories, which we'll discuss now, which have multiple power counting parameters within themselves. So the important thing, whenever you design an effective field theory, the first thing you have to do is to figure out what the power counting parameters are, because that will push you in the direction of where you need to go, right? So let's first talk about the physics, and then we'll talk about how we're going to design an effective field theory to describe the physics. So let me first give you a 5-minute introduction to gravity wave physics. So you all know about the LIGO detector. So this is a plot of what's known as the LIGO bucket. This is, on the x-axis we have frequency, and on the y-axis we have the sensitivity detector or the strain. So here's something to think about. So the LIGO detector, when a gravity wave comes through, the mirrors move by 1 part in 10 to the minus 28. Okay? So if you calculate that, given the length of the arm, it's orders and orders of magnitude smaller than the radius of the proton. So this should give you pause, because you'd say, how can you possibly detect motion of a mirror at distances less than the radius of the proton? Because clearly there are fluctuations on that order from all sorts of things. Think about that, and we'll see if you can come up with an answer by tomorrow, and I'll give you the answer if you can't. So this is about 1 hertz here, and this is about 1,000 hertz. Okay? And so those of you who have ever, I was going to download, maybe tomorrow I'll download it for you, what the signal sounds like if you convert the signal into sound. You probably all heard it. How many people here have been at a seminar colloquium about gravity waves? Oh, really? That's interesting. So not only about half of you. Okay. So the inspiral, so just the basic physics of it, if you have 2 compact objects and they're rotating, and as they rotate, they radiate, and as they radiate, they lose energy, and as they lose energy, the orbit starts to collapse. Okay? And at some point, it reaches what's known as the ISCO. So the ISCO is the innermost stable orbit. I don't know what the C stands for. So if in general relativity, if you look at the solutions to Einstein's equations, if you calculate the geodesics, then at some r, there's no stable orbit, no matter what you do. So what happens is that if you ignored radiation, then you have these solutions which are, we can just look at the circular ones with no ellipticity, And at r gets too small, it's just there's no stable orbit anymore. It just goes away. So what happens is that the binaries are captured, and over time they start to speed up. And then once the r gets too small, it goes straight in, right? And the plunge frequency, which is the frequency at the time of ISCO. So F plunge scales like 1 over m, where m is the mass of the system. Okay? So as the mass gets larger, it doesn't stay in the LIGO bucket for very long before it plunges. So for large mass systems, so if you remember, the original discovery was on the order of 30 solar mass objects, right? So that's considered a large mass, and those guys only lasted fractions of a second inside the detector. And of course, you've all heard about the kilonova event. So those are neutron stars, which are less massive, and they stayed in the bucket for tens of seconds. Okay, because this mass is small enough, the plunge frequency got moved out here, and those are much more easily studied. So what determines what cuts off this LIGO bucket, and that is what the background noise is. So the limiting factor here is seismic, and here it's quantum or shot noise. Okay, so this is much easier to push back than that. So one way they try to push this back is to move things underground, or of course to go into space. So the ELISA, which will be built in Europe, will push this back way back here and be able to look at really massive objects like black hole inspirals involving black holes at the centers of galaxies and things like that. So that when that happens, and the number of events there is supposed to be enormous. So that's going to be a game changer when it happens. Okay, so the goal of the scientific program is, given there's going to be some signal which has some frequency and wavelength, and amplitude, I should say, and you've all probably seen the pictures of what the signal looks like, and you have to have a theoretical template to match onto. And the signal will depend, obviously, it'll depend on the masses. So this is a function of the masses, the spins, and in principle, where I means the internal structure of the object. So to me, the most interesting part of this science is to figure out I. This is not unlike what we do in particle physics when we try to discover what's the underlying ultraviolet physics given the long distance physics. Of course, there's a huge amount of information here, M1, M2, and S. So what are the typical masses of black holes? What are the typical spins of black holes? How are they populated? Where are they populated? So there's a host of astronomical science that can be done. But for theoreticians such as ourselves, we're probably more interested in here. You know, how does a black hole behave? What do the internal dynamics of a black hole look like, if that makes sense? What is the equation of state of a neutron star? That, in principle, is encoded in this data, and our job as theorists is to figure out how to extract that information. And I'm going to show you how we use effective field theory to do that. Okay? So the early stages of the inspiral are non-relativistic, and so V will be small, and our expansion parameter will be V. Furthermore, the early stages of the inspiral, the space is approximately flat, right? Gravitational nonlinearities will be controlled by V. Right? So we're going to build an effective field theory based in at least multiple expansion parameters, but the most important of which will be V, perhaps, and that's called the post-Newtonian expansion. So you do corrections to Newtonian physics due to the nonlinearities of gravity. And our goal will be to build an effective field theory with that as our expansion parameter. So, so let's talk about the scales involved. So whenever you build an effective field theory, the first thing you do is figure out the scales. And if you have large ratios, then you can use those ratios, or small ratios, you can use those ratios as your expansion parameters. So what are scales in this theory? Well, we have multiple scales. One is r, which is the radius of the compact objects. And we've already encountered this one when we did our point particle theory. And in fact, our first approximation will be when these guys are far enough apart, they just look like point particles to each other, right? So this is r here. That's the size of the object. And then we have, that's in isolation. Then we take our two objects and we put them in orbit, and we have little r, which is the radius of the orbit. And finally, we have the wavelength of the radiation. So the radiation wavelength which is going to go like the period of the orbit, goes like r over v. So remember, v is r times the radius times the frequency. So that's the period. Right? So we have a hierarchy. We have r is much, much less than r, little r, and little r is much, much less than the frequency, the wavelength of the emitted radiation. Okay? So as long as v is much less than 1, then we should be able to form an expansion in V. Actually, we'll have multiple expansions. So our expansion parameters will be R over R and V over C. And because we're high energy theorists, there's one other very, very large or very, very small expansion parameter, and that is h bar over the angular momentum of the orbit. That's pretty small. So a relativist would never even consider this, but the reason we use this is because we draw Feynman diagrams, right? And you'll see that everything we calculate will be with Feynman diagrams, and we want to throw out all Feynman diagrams which are quantum mechanical, right? So all the quantum mechanical corrections will be suppressed by h bar over L. So even though physically it's ridiculous to think about this, what this is telling us is that we're going to throw out all diagrams that have loops, right?
So in this treatment, you're not able to capture what happens right before they
Correct. So as soon as V becomes order 1, the effective field theory will break down and you lose control of the calculation. Absolutely. So so for instance, the first few sightings, observations were made with very massive objects. There was no time in which they were inside the detector where V was small. So you could say, well, how did we do anything with that? And the answer is it's all numerical. So then you could say, if you could do it numerically, then why do you care about doing anything analytically? Well, first of all, we're theorists, so that's the blunt answer. But actually, there's an important practical matter, and that is that it's very computationally intensive to do these these calculations. And furthermore, at early stages, where you're studying the system over many orbits, the computers, it's too computationally intensive to do it. Also, the error grows as you the computational error grows as you do in more and more orbits. So actually, in practice, what they do is they take the theoretical post-Newtonian calculations for the early stages. For the late stages, they use the computer simulations, and in the middle, they use some modeling called what's called the EOB, or effective one-body method, and that's sort of a way of interpolating between the two, and then they match them together into a smooth, and it works remarkably well. So if any of you have seen the fits, the theory fits to the waveform, it's remarkable. So. Yeah.
So what about the spin of the object?
Yes.
The two pulsars.
Yeah, absolutely. So the spin of the objects, so it typically for a maximally rotating black hole, the spin will start to play a very important role. And we'll be able to calculate, so one of the things I've been involved with is calculating how the spin affects the signal. And we'll talk, I don't know, actually I don't think we'll talk about that because we simply won't have enough time. But the spin, you put in the effective field theory just like we put the spin in the theory of our rotating springs. Okay. So let's build an effective field theory for this description. And instead of jumping to the full problem, let's work with a baby toy model first, which is always a useful thing to do just to get your feet wet. So let's just look at classical electrodynamics and consider a comparable toy model. So let's consider two charged spheres and ask ourselves, can we understand the dynamics of two charged spheres? Okay? So let's write down an action for two charged spheres. So we're going to assume, again, that this R is much greater than this R. And also, let's keep Lorentz invariance in the game. Let's allow this to be a Lorentz invariance system. And then later on, we will take the large C expansion. So what does the action look like? So the first step is we're going to make an approximation where R is much bigger than big R. And we're going to treat as point particles. Right? So our action is going to look like something like, S, the usual one, plus some S, which is down by, includes pieces which are down by R over R. And we'll call these the finite size effects. Right? Just like we did in our Coset construction. Okay? So this is an infinite series in R over R, and we'll truncate that series depending on how accurate we want our predictions to be. Okay, so S0 we know. We've already worked it out with the Coset construction. We did it non-relativistically, and if you do the relativistic generalization of it, so S0 sum over minus sign. So if you were to do the relativistic coset, that's what you would find. This is nothing but m d tau. the proper time, right? So if I parameterize my world line, so x mu of lambda is the world line, right? And lambda tells you where you're sitting on that world line. We could choose to parameterize that world line by the proper time tau if we wished, right? And then this would just become md tau. Okay? So that's what you would find. And now let us add some finite size terms. So we actually don't have to go through the Coset construction to do this, because we have enough symmetry as is. So the finite size corrections. So this is all discussed in the notes that should be online. Okay. So and in much more detail than I'm going to go here. I'm going to have to pick and choose subjects. So there's all sorts of stuff in there that I won't have time to cover, and there'll also be all the details which I leave out. Okay. So what symmetries we have to, so let's impose our symmetries. Well, one, we have Lorentz invariance, right? And we also have another symmetry which we haven't discussed yet, which is called reparameterization invariance. Let me explain that to you. And that's just a statement that it shouldn't matter what parameter I choose to parameterize my line. So if I took lambda goes to f of lambda, then the action should be invariant, right? So this is called reparameterization invariance, and that's actually called RPI. And that's an important symmetry. It's not really a symmetry. It's more like a redundancy in many relativistic effective field theories. And finally, of course, we have gauge invariance. Okay? So let's write down the first operators that we can, which are leading order in big R over little r. Okay? So first it has to be gauge invariant, right? So the only gauge invariant object we can construct in QED is F, right? And we have to make something Lorentz invariant out of it. So what can we do? So S finite size. We have our integral over this, and we can write down F mu nu, and then we have to put in some parameter in front of it, which I call C1. And this, so I should actually put an I here for parameterizing with the world lines. So there's actually mi lambda I. There's an I labeling all these things, right? I is 1 and 2. Let's call this particle 1, and we'll call this particle 2. Okay? Now, if we want to make it invariant under reparameterizations, then I have to put in a factor of v squared, where v mu is dx mu d lambda. And so this is just the fact that when you change parameters, the measure is going to change, and the variation of the measure will cancel with the variation. You can sort of see it off the top of your head here, because this goes like d lambda, and this goes like 1 over d lambda. So all the lambda dependence will cancel. So if you made this transformation, it would leave this action invariant. Yeah. So it depends if you want to allow for parity symmetry breaking. So we're going to say that parity is a good symmetry. So there's one other term that we can write down, which looks like this: v mu f mu nu f nu rho v rho. And in this case, we have to put in a 1 over the square root of v squared. So there's an I here also to label the particle. Okay? And that is the only thing that you can write down at the leading dimension, right? So by dimensional analysis, you can figure out that these guys scale some power of big R, right? So they actually both scale like R cubed if you work it out. Okay, so these are the leading order finite size effects.
In the second term, all the indices are I, or I mean lower.
So this I is labeling the particle number. That's not a space-time index. And this mu, these are the space-time indices that all get contracted. Yeah, so there's a sum over I here for the two particles. Yeah. Yeah, there's a sum here over I. There is. Thank you. Let's call it C2. Okay. So it's an interesting question to ask physically what are these coefficients. So if you were to write this out in terms of E's and B's, you would have two terms, one which goes like E squared and one which goes like B squared. Okay? And remember, these all sit on top of the world line. So what do these physically correspond to? Well, if I were to put the system in a background field, so if I replaced F by a background plus the correction, they would just generate a field. In other words, they would if I made the replacement F goes to F bar plus delta F. This is the background field. Then this will generate a term on the world line that just looks like some number times delta F. Okay? So all that does was, so for those of you who know some field theory, this would be just like it would give the external field a correction to a 1-point function, to an expectation value. That would be saying as if the particle had a field itself. Let me explain further. When we couple to the electromagnetic field, we have to add the term due to the charge, which I didn't do. So there's also plus Qi V mu A mu d lambda I. So this is the coupling of the particle to the electromagnetic field. So this looks like just an V, the world line has a charge, it generates an electromagnetic field, right? By the way, so if you want to, so why is this gauge invariant? Doesn't look it. A mu goes to A mu plus D mu chi. Okay, so let me explain that. So why is that term gauge invariant? So we have something like d lambda dx mu d lambda. A mu under a gauge transformation goes to d lambda dx mu d lambda. A mu plus d chi dx mu. This is way too many things that look like x's. So that's an x. This is, let me not call it chi, that would be smart. Let me call it phi. Okay? So, yeah. This guy is a partial derivative with respect to x mu. So actually it doesn't really matter here because nothing explicitly depends on those coordinates. But so now you could see that this term goes like by the chain rule, it's just d by d lambda on phi. So this term becomes d lambda. That's the total derivative, so I can just drop it. So if you wish, it's a Wess-Zumino term. Changes by total derivative. So so the reason I wanted to, well, first of all, I should have put that there to begin with, but the reason it came up now is because what does this, so this is telling you the field, the world line is generating a field because it's coupling to the field. If I put this system in a background F bar, it generates a term which looks like F. Right? Remember, this is the background. That's a non-dynamical object. This is F. So now it looks like it has a charge. So what does that mean? I take the system, I put it in a background field, it deforms, and when it deforms, it generates a multipole moment, which then generates a long-range field. So these coefficients, Ci and Ci1 and Ci2, are nothing but the electric and magnetic polarizability of the system. Okay? And there's going to be gravitational analogs for black holes, called, and if you've taken an astronomy course, called the Love number. So astronomical objects have deformabilities, gravitational deformabilities. Those are called Love numbers, or tidal Love numbers. So this captures the fact that our approximation, our point particle approximation, is inexact, right? Because if it were a point particle, you couldn't deform it. You need to have a finite size object if you're going to deform it under an external field. Okay. So that is stage one of this effective field theory, because we have not considered, so far we've only considered the scale big R, and now we want to allow the two objects to interact with each other. Now the nice thing about this particular problem is that it's solvable exactly at leading order in the finite size corrections. Yeah.
So these finite size effects scalars are
Yeah.
which are smaller or
Big R, the size of the object. Yeah.
yeah, so they're finite size effects.
Right. So when R goes to 0, they vanish. Okay. So now a little bit of field theory. So now let's calculate the energy of the system for these two guys, say, being captured in some arbitrary orbit. So the way we're going to calculate, how do we calculate the waveform for the black holes? So just to come back for a second so we can understand why we're doing this. You've got these, so how do we calculate the waveform? Well, what do we need to do to know the waveform? We need to know the trajectories of the particles. Because given the trajectories, we can calculate the radiation. So the way we calculate is we calculate the potential between them, right? Which will depend on the masses and the velocities and the spins. Once we have the potential, we solve the equations of motion to find the orbits. Then once we have the orbits, we use the orbits to calculate the radiation. So it's a two-stage process with a slight important caveat that there's something else, and that is not only do you need to know the potentials, but you need to know how fast the radiation is causing you to lose energy. So there's something called radiation reaction forces. So when something radiates, it loses energy, and it pushes back on the system, and that affects the orbit. So we like to think that there's just solving the equations of motion and then calculating the orbit, but there's a little bit more to it, and calculating the radiation, because the radiation then changes the equations of motion, and we have to feed that back on the system. But for the moment, let's start with the simplest thing. Let's calculate the orbit and let's ignore radiation reaction, and then we'll calculate the radiation. To calculate the orbit, we need to calculate the potential. What is the potential? It's the energy of the system. Okay? So how do we calculate the energy of the system in field theory? So in the original, so the approach that, so this was done, my work on this was done with Walter Goldberger. So when we built this effective theory, we used completely quantum field theory approaches to the problem, even though this is a completely classical problem. Only because quantum field theory gives us intuition and systematics that are very useful. In addition, as I'll talk about before these lectures are over, you run into divergences, classical divergences. And what field theory does, what quantum field theory does, is we know how to handle divergences. They're called counterterms, right? And so by organizing the system in terms of a Lagrangian and effective field theory, we know exactly what to do with these divergences. And this is actually what motivated us when we first started working on this problem, because there was this issue of divergences in the relativity calculations that were complicated. And we realized that if we did things from a field theory standpoint, quantum field theory standpoint, we know how to handle them. But what's also interesting is that it also teaches us as field theorists, as high energy theorists, important part is that there's nothing inherently quantum mechanical about the renormalization group. The renormalization group is just the idea of how things change with scale. And there's nothing fancy quantum mechanics about it. It's very simple. And we'll see, in fact, how logarithms, so those of you who have taken enough field theory know that you sum, when you run the renormalization group, you're summing infinite logs. And the renormalization group will allow us to actually generate a whole series of logs in the predictions. Okay, so the next thing we're going to do is we're going to calculate the potential. And the way we're going to do that, how do we calculate energy in a field theory? So if we look at, so if we have some generic partition function, this, and I hope this is familiar to you. This is the partition function. J is our source. In our case, our sources will be our particles. And if J is changing adiabatically, then we can extract the energy by calculating the partition function. Okay? But this, Feynman diagrammatically, this just means calculating vacuum bubble. So this is the vacuum to vacuum correlation function in the presence of a source. Okay? So all we're going to do is calculate vacuum bubbles. And the word bubbles here is very misleading because there won't be bubbles. And this will give us the energy or the potentials of the system. So we know how to do that. Everybody here probably has lots of experience with Feynman diagrams. So we'll start calculating Feynman diagrams. And those Feynman diagrams will allow us to read off the energy. And then eventually we'll use Feynman diagrams to also read off, to be able to calculate the radiation. Okay? Questions?